Okay, so in this video we're going to start topic 4.5, which is the last topic in the waves unit. And 4.5 is about standing waves. Okay, unlike the last topic, which was wave behaviors, 4.5 is much shorter, and it'll be much quicker to explain the concepts and get through this topic. So, what is a standing wave? Well, a standing wave, unlike a traveling wave, is a wave which appears to not be moving. Okay, and so I am going to link a site in here, and actually, let me show you what this looks like. Okay, but this is a page from the physics hypertext book, and you're welcome to read this whole page because it's all stuff you probably need to know about. But really, I just want you to see this image right here. So on the left side, we have what's called a traveling wave, which is exactly what it sounds like. A standing wave is a wave which appears to not be moving. Okay, and so this would be an animation of a standing wave. And again, I'll link that in so you can read as much of that as you want to. It's all pretty interesting and relevant information. If you're just sick of how your textbook explains things, I would encourage you to read more about that, but really I just wanted you to see that animation there. Okay, and basically a standing wave is a wave which can be created in situations where you have two reflected waves continually superimposing at certain frequencies. And so essentially you have a situation where you somehow create a wave and it reflects off of a boundary, and as that wave comes back, the new wave that you are creating causes interference with the reflected wave, and that can create a standing wave. Okay, so I'm also going to link two short video clips so you can see what that looks like. The first one is created with a machine that basically moves a string at a certain frequency, and the second one you can see is done with a person where he basically ties one end of either a rope or something, and he uses that to create different types of standing waves, and you'll see how that works. And again, the principle is that the reflected wave comes back and combines with the new wave going in, and because of superposition, if the frequency is just right, you can create what's called standing waves. And so that is the idea of 4.5. Okay, so the essential idea in this topic, when traveling waves meet, they can superimpose to form standing waves in which energy may not be transferred. There's actually a lot of really important applications to this that you'll see here in a few minutes. This is a pretty short unit. Just to give you an idea of what you need to be able to understand, you have to understand the nature of standing waves, you have to understand boundary conditions, which we'll spend time talking about, and then nodes and antinodes. As far as what you must be able to do, you must be able to describe the nature and formation of standing waves in terms of superposition, which is what I just did a minute ago. So if you need more clarification about that, I would encourage you to read the first little bit of your textbook or the hyper physics textbook that I linked before. That's really easy to explain how those are formed because of superposition. Distinguishing between standing and traveling waves, that's not difficult at all. Observing, sketching, and interpreting standing wave patterns in strings and pipes, that's something you'll become pretty familiar with. And then solving problems involving the frequency of a harmonic, length of the standing wave, and the speed of the wave. And that's something that's also very straightforward to do. It all comes down to the wave equation, essentially V equals lambda times frequency, wavelength times frequency. And so we'll see problems like that. Okay, just some general guidance from the IB. Students will be expected to consider the formation of standing waves from the superposition of no more than two waves. Now, technically speaking, you can have superposition between any number of waves that you want. And in fact, we kind of talked about that before. There's something called Fourier series, where you can approximate any function as the infinite sum of sine and cosine waves. But the IB doesn't require you to know about all that stuff, and so we're only going to be dealing with superposition of basically two waves. Boundary conditions for strings are two fixed boundaries, fixed and free boundary, and two free boundaries. Basically, there's two situations where we will deal with standing waves, either for strings and for pipes. Okay, and so this is basically just telling you under what conditions do you need to be able to solve those types of problems. And so you can read that for yourself. For standing waves and error, explanations will not be required in terms of pressure nodes and pressure antinodes. Alright. And as you're thinking, like, what does that mean, strings and pipes? It helps if you think in terms of musical instruments. And so, for example, a standing wave with strings would be like, a standing wave on a guitar string or a violin string, something like that, or like in the videos I linked before. Whereas pipes could be like an organ pipe or a clarinet or a flute or something like that. The lowest frequency mode of a standing wave is known as the first harmonic by definition, and the terms fundamental and overtone will not be used in examination questions. Okay, so when we talk about the fundamental frequency, that is the same thing as the first harmonic, and that's just something that you need to know. Now, there's no equations given to you under 4.5, so you must be able to derive all standing wave formulas. Or I guess you could memorize all of them. I mean, some people do that too, but that's up to you. Alright, so let's go on a little bit and just talk about the basics. Okay, so here we basically see where we have two waves, a red one and a blue one, and they're going towards each other. And because of superposition at every point along the, let's say this is a wave on a string, for example. At every point along the string, you get superposition. Okay, and so the red wave that's flipping back and forth in the right animation, that is the superposition of the red wave, or of the blue wave and the green wave. And so you can see if the two waves going towards each other happen to be going at just the right speed and just the right frequency, then you can get the standing wave effect. Okay, and so before, when I said a standing wave is a wave which appears to not be moving, understand that, as you can see in this animation, there are waves moving on this animation. It's just because what you're actually looking at is the superposition and not the individual waves themselves. The overall effect is it appears that there's no motion of the wave, even though it's actually the superposition of two waves which are moving. Okay, so the red wave is the superposition wave. That's what we would call a standing wave. Alright, so I'm going to go to the next slide because that slide is annoying me. So let's go through the notes. You may be wondering how a situation could ever develop in which two identical waves come from the opposite directions. And so the analogy we're going to use is, think when you plug a stringed instrument. Okay, so imagine like a guitar string. When you plug a guitar string, basically from your finger, waves go out in both directions. And when they get to the end points of the guitar, they are going to reflect and they're going to go back towards each other. And as they pass through each other, we know what happens when waves pass through each other. They experience superposition. Okay, and under the right conditions, this can form a standing wave. Okay, so here we have a string and the length is L. Okay, and what you're seeing right here is basically the simplest type of standing wave where it just goes back and forth in the middle. And this is actually what we will call the first harmonic. This is a type of standing wave that appears on the string that basically has the lowest possible frequency. And so the first harmonic for a string just kind of goes back and forth like that in the middle. It says there's two nodes and one antinode. We'll define that on the next slide, what a node and antinode are. But basically, the nodes are the parts of a standing wave which appear to not be moving, and the antinode is the point on the wave that appears to be moving the most. Okay, so in other words, here the two endpoints are the nodes, and the middle part, the one that's going back and forth the most, is the antinode. Now, what that actually means, remember standing waves are formed from superposition, so what that actually means is that the nodes are the points where the wave can't move, and so typically that's where you would get destructive interference between those two waves superimposing with each other. And the antinode would be the point on the wave, or on the string, where the two waves going towards each other, where those experience constructive interference, and that's why the amplitude is the greatest at that point. And so here we have two nodes, or two antinodes and two nodes and one antinode in the middle. Now, in this case, the reason we have antinodes has to do with what's called the boundary conditions. Boundary conditions just means what is happening at the edges of the problem. So in this case, the boundary, the two boundaries that we're talking about are the two ends of the string. Why do those have to be nodes? Well, because they can't move. Why can't they move? Because they're physically tied down. I mean, anyone that's ever played a string instrument like a guitar or violin knows that the two ends are tied down at the end. Okay, so there's a physical reason why they have to be nodes. Okay, this slide right here just kind of goes over nodes and antinodes again. Okay, so add that to your notes. It is important that you know that nodes and antinodes always alternate. Remember, what you're actually talking about here are areas where you have constructive interference and destructive interference. Okay, so you would have, at a node, you would have destructive interference, and at the antinodes, you would have constructive interference, where those two waves add together and form the biggest possible superposition. Notice that this standing wave looks different than the one we saw before. Okay, and so this is actually a higher harmonic, and we'll come back to harmonics later on. Okay, but notice that nodes and antinodes always have to alternate. Okay, now the secret to solving problems with standing waves is simply understanding the boundary conditions. And I said this before, but boundary conditions basically set limits at the end of the situation. For example, the boundary condition for a wave on the string is that the two endpoints are fixed and have to be nodes. And again, there is a physical reason for that. Okay, so if you understand how to apply boundary conditions, then problems with standing waves are typically very easy. Now, before we get too much into solving problems with standing waves, I want to take some time and introduce you to the applications of standing waves. And so I'm going to link some videos that I want you to check out that talk about the applications of standing waves and how they are applicable in music and microwaves and just generally on strings. Those are more just for demonstration purposes. So check out these videos, and I will ask you some questions about them in just a minute. Okay, so hopefully you enjoyed those videos. We're going to go ahead and stop the video here. In the next video, we're going to kind of get into the details and see what standing waves look like for strings and for pipes and how to apply the wave equation with certain boundary conditions to solve problems with standing waves. And it sounds kind of complicated, but really, once you see what the patterns are and once you understand how to set these problems up, it's a very straightforward type of process. And so the next video is hopefully not going to be too long. As always, please let me know if you have any questions, and I'll see you guys in the next video.